The SpaceX Raptor engine is not just another rocket engine. It represents a fundamental shift in how propulsion systems are designed for the future of spaceflight. At its core, Raptor is built around a very deliberate decision, using methane instead of traditional fuels. Most legacy engines either relied on hydrogen, like the RS-25, or kerosene-based fuels like the Merlin Engine. Methane sits right in between these two extremes. It offers better density than hydrogen, which reduces tank size and structural penalties, while also burning much cleaner than kerosene, avoiding carbon buildup inside the engine. That single decision directly supports long-term reusability. But fuel choice alone doesn't define Raptor. The real breakthrough lies in its cycle architecture, full-flow staged combustion. This is where the engine moves into an entirely different class of engineering complexity. Instead of partially burning propellants like traditional engines, Raptor routes both fuel and oxidizer through separate preburners. One runs fuel-rich, the other oxidizer-rich. By the time they reach the main combustion chamber, both propellants are already in a gaseous state. Nothing enters the chamber as a liquid. That changes everything. This approach allows the engine to extract maximum energy from the propellants while also reducing thermal stress on the turbines. In simpler terms, it increases efficiency while simultaneously improving durability, something that usually involves a trade-off in rocket design. However, this design comes with serious challenges. Running an oxidizer-rich preburner at high temperatures creates an extremely aggressive chemical environment. Oxygen at those conditions can destroy conventional materials. So the engine depends heavily on advanced metallurgy and precise thermal control to survive. Another defining feature of Raptor is its extremely high chamber pressure. Higher pressure means better combustion efficiency and higher exhaust velocity, which translates directly into performance. But pushing pressure to these levels introduces mechanical stress, thermal gradients, and instability risks that are very difficult to manage. To handle this, the engine uses regenerative cooling. Methane is circulated through channels in the chamber walls before it is burned. This absorbs heat and protects the structure while preconditioning the fuel. It's an elegant solution where the fuel doubles as a cooling medium. Then comes the turbomachinery. Raptor's turbopumps operate at extreme power densities. They spin at very high speeds and handle fully gaseous propellants coming from the preburners. Managing flow stability, preventing cavitation, and ensuring long operational life under these conditions is a major engineering challenge. The full flow cycle actually helps here. Because both propellant streams drive turbines, the thermal load is distributed, reducing peak stress. That's critical for reuse. Unlike expendable engines, Raptor is designed to fly multiple times with minimal refurbishment. Combustion stability is another problem that becomes more difficult as performance increases. At high pressures, even small disturbances can create oscillations that damage the engine. Raptor addresses this through highly refined injector design and precise control of propellant mixing. The goal is to maintain a stable burn even under extreme conditions. All of this is tied directly to its role in Starship. The engine is not designed as a standalone system. It has to operate in clusters, throttle deeply for landing, and maintain reliability even if one engine fails during flight. That level of integration requires tight coordination between propulsion, structures, and control systems. When compared to older engines, the shift becomes clear. Traditional designs often prioritized either performance or reusability. Raptor is one of the first engines to aggressively pursue both at the same time. This is why the engine matters beyond just its technical specifications. It represents a transition toward systems that are not only high-performing, but also sustainable in terms of cost and operations. From an engineering perspective, Raptor is where thermodynamics, fluid mechanics, and materials science are pushed to their limits and forced to work together. It is not just an improvement, it is a redefinition of what a rocket engine can be when reusability becomes a primary design constraint rather than an afterthought.